Hello, welcome to Chapter 7, Part 4, Rotational Dynamics. So in this part of the lecture, we're going to be applying Newton's second law in rotational form. So by now we're very familiar with Newton's second law, F equals ma, or net force equals ma, which corresponds to the linear form, in other words, for objects moving in a straight line. In this form, the net force is what causes the acceleration A, and the mass of the object represents inertia or resistance for the object to accelerate. In this part of the lecture, we're going to be using Newton's second law in its rotational form, where the net force is replaced by the net torque, the linear acceleration A is replaced by the angular acceleration alpha, and finally the mass or inertia m is replaced by the rotational inertia, which is also called the moment of inertia. So this is Newton's second law in the form we're going to use it in this section. The net torque is equal to I times alpha. So what this law says is that a net torque causes an object to rotate and to accelerate in an angular fashion with an angular acceleration alpha. And furthermore, the object has rotational inertia that tends to be a resistance to this acceleration, meaning that the more rotational inertia there is, the harder it is to get the object to rotate. So rotational inertia is the resistance of an object to angular acceleration. So what we're going to do in the remainder of this lecture is just work through a bunch of examples showing different applications of rotational dynamics. And in all cases, we're going to be using Newton's second law in its rotational form. So let's start out with a fairly basic problem here, the spinning of a compact disc or CD. So we're told that the motor in a CD player exerts a torque of 7 times 10 to the minus 4. The CD has a diameter of 12 centimeters and a mass of 16 grams. The question is, what is the disk's angular acceleration? All right, so in order to use Newton's second law, which remember is net torque equals I alpha, we're going to always have to figure out what the rotational inertia is for the object I. So in this case, we've got a disc-shaped object. So what we have to do is go back to the table from the previous section where we look up various shapes and find the correct shape. And a compact disc is basically a solid cylindrical object. So this is the object we're going to use. Obviously, a CD or a DVD is a very thin cylinder, right? This dimension here is very short, but it is indeed a cylinder. And so for a cylinder, the rotational inertia is 1/2 mr squared, where m is the mass and r is the radius. Now the radius is of course half the diameter, so the radius in this case is 6 centimeters, and we have to convert that to meters, so that's 0.06 meters. So that we can go ahead and the first step here, let's calculate the rotational inertia of the CD. So I equals 1/2 mr squared. Now remember, mass is in kilograms, so 16 grams is 0.016 kilograms, and we just said that the radius is 0.06 meters, and remember that is squared. So this comes out to be 2.88 times 10 to the minus 5 kilogram meters squared. Now just a note here, this number obviously is very small. 10 to the minus 5th is 1 over 100,000. So this is a very small rotational inertia, and that's not a surprise because we're talking about a very lightweight plastic disc that is going to be very easy to turn. So it's not going to have a lot of rotational inertia, and we can see that in this number. So now we can apply Newton's second law. Net torque is equal to I alpha. And there, we're going to solve, we want to figure out what the disk's angular acceleration is, so we solve for alpha. Alpha is equal to the net torque divided by I. The net torque was given in the problem as this number right here. So that's just plugged in up here in the numerator. And I, we just calculated up here in step 1. So, this is obviously a problem for your calculator using scientific notation. The answer ends up being 24.3 radians per second squared. Here's another example of rotational dynamics. An amusement park exhibit has a large solid granite sphere with a mass of 25,000 kilograms and radius of 0.8 meters that floats frictionless on a thin layer of water. If the child pushes upwards with 80 newtons of force, what is the angular acceleration of the sphere? So we can kind of get a picture of what's going on here. You may have seen something like this in an amusement park or a town square or something. They have a large sphere here, and it's there's water pressure under here that basically makes this thing float. So it really doesn't have any friction per se. The friction would be very negligible, but obviously in this case, this giant sphere of solid granite has a very large mass of 25,000 kilograms. But nonetheless, even a small child like this, by pushing up against it, can create torque to get this thing to turn, all right? However, we can kind of guess that this child's not going to be able to rotate this thing very quickly. So it's probably going to have a very small angular acceleration. But let's go ahead and do the math. So let's calculate the rotational inertia. And again, this is a solid sphere. So we look this up in the table shown in your textbook or in the previous section of these notes. And for a solid sphere, the rotational inertia is 2/5 mr squared. So 2/5 is 0.4, the mass is 25,000, and the radius was given as 0.8 meters. So that comes out to be 6,400. And obviously, this is a large number. We would expect that from something as massive as this big sphere of solid granite. The torque, we're told, can be calculated. Remember, torque is R times the perpendicular force. So the radius is the radius of the sphere, right? This child is pushing upwards. Here's a picture of the situation. Here's the sphere. Here's the sphere's radius is 0.8 meters. That was given. And we're told the child is pushing upwards with 80 newtons of force. So since these two, the R and the F, are at right angles, we can just multiply them together to get the torque, and the torque is 64. Now, Newton's second law, net torque is equal to I alpha. Let's solve for alpha. Alpha is equal to net torque divided by I, so we have 64 divided by 6,400, and that gives us our angular acceleration of 0.01 radians per second squared. So as we predicted, this number is very small. This sphere will rotate and accelerate, but it's going to be a very small, slow acceleration because of its large rotational inertia. In this next example, we're going to calculate the acceleration of a lightweight beam balance. We actually looked at this problem in one of the previous sections of this chapter, but we didn't calculate the acceleration. We just found out what the net torque was and which direction it rotated. But now we want to also calculate what is the alpha, the angular acceleration for this system. So the situation is we have a 6-meter long lightweight pole. Now remember, when we say lightweight here, we're going to ignore the mass of this pole. So you can think of it like a thin, hollow tube. And at the end of the tube is our two heavy masses. So we have a 20 kilogram mass over here and a 60 kilogram mass over here. You can see this this dimension here, or distance, is 2 meters from the pivot out to this 60 kilogram mass. Therefore, we know that this distance must be 4 meters because the whole thing is 6 meters. So let's go ahead and solve this problem, figure out which way does it rotate and what is the angular acceleration. So we already did this these first couple of steps here in the last section, but just real quickly, I'll review it here. Each of these masses creates weight equal to mg pointing down. And so they are going to generate a torque that's going to make this beam rotate either clockwise or counterclockwise, depending on which of these torques is greater. So we're going to find the net torque. So the first thing we can do here is notice that this torque here would tend to rotate the beam counterclockwise. So that's our positive direction. That's our positive torque. So torque is equal to the radius or distance times the force. So we have 4 meters here times m1g, all right, and down here I plugged in the mass is 20, and g is 9.8, and then we have to subtract this torque because it's going to move this thing, it's going to try to move it at least, in the clockwise direction, which is, remember, that's a negative direction for rotation. So we're going to subtract 2 meters, that's this distance, times the weight force here, which is m2g, and m2 is 60. So our torque, it turns out this number is larger than the first number, so our net torque is negative, and it's negative 392. So since that's a negative torque, it will rotate clockwise. Okay, and so again, this was just a review. We did this much of the problem in the previous part of this lecture. So let's go ahead and continue the problem now and find out what the acceleration is of this beam balance. So in order to do that, we're going to, of course, end up using Newton's second law again. We have to know what the I is, the rotational inertia. Now, there are 2 masses here. So remember the way we calculate the rotational inertia for 2 masses. We just add the rotational inertias for each of them together. And we did this something like this also in the previous part of this chapter's lecture. So the total I is m1 r1 squared, all right, where this is m1 and this is r1. And then we add to that m2 times r2 squared. This is mass 2 over here. This is r2. So plugging in our numbers, we get 20 kilograms times 4 meters squared plus 60 kilograms times 2 meters squared. Now remember, rotational inertia is always positive. We don't use signs. We don't have to worry about direction or anything like that. So they're always positive numbers. We add those together, we get 560. Now we can use Newton's second law, solve for alpha, which is the angular acceleration. It's torque divided by I, rotational inertia. So our torque is negative 392 from the last slide. And I, we just calculated to be 560. So that gives us an angular acceleration of negative 0.7 radians per second squared. So what does this mean? Well, the minus sign, again, tells us that this thing is going to accelerate in the negative direction, which is in the clockwise direction, all right? Because remember, this heavy weight over here has created a larger torque than this lighter weight over here, and therefore this thing is going to rotate in the clockwise or negative direction. So now let's modify this problem a little bit, and let's do it for a heavy beam balance. In other words, the only difference between this problem and the last one is now we're going to assume that this beam here is a big, heavy, thick piece of wood, a long board that has a mass of 45 kilograms. And so we can't ignore the mass of this board anymore. It's obviously going to create torque, and it's going to affect the way this beam balance rotates. So again, we did the first part of this problem in the previous part of this chapter's lecture, but we'll go ahead and redo that. So the key thing here is the only difference between this problem and the last one now is that, remember, this heavy beam, we have to model it as its gravity force, its weight right here, acting on its center of gravity. Okay, that's the trick. Whenever we have a long extended object like this, we put all of its weight acting at the CG point. Now, how do we know where the CG is? Well, it's actually very simple. This is just a long board. So the CG is exactly halfway across the board. That's, remember, like the balance point. So if the board is 6 meters, then we know the CG is 3 meters from each end. Okay, so in the way you can see the dimensions here, remember this was 2 meters, so this distance here must be 1 meter to get the total 3 meters. So when we add up our torques, we're going to get, again, this force, or I'm sorry, this torque here is positive. That's because it's in the counterclockwise direction. But now we've got this torque as well. The weight of the beam or the board is creating a positive torque because it would try to rotate this thing in the counterclockwise direction. So we've got 1 meter is its R, and we've got mass of the board times G. And remember, the mass of the board was 45 kilograms. And then this torque over here is still negative because it's trying to rotate it in the opposite direction. So we have -2 times m1g, which is the same numbers that we saw in the last problem. So the difference is, of course, this term here, but this term is positive, and you can see when we add all these, we have to multiply these all together and then add up the terms, we now get a positive torque. So this thing is now going to rotate counterclockwise in this direction. In other words, adding the weight of this board, and you can see there's a lot more board over here on the left of the pivot compared to the right. So this is going to shift the balance. And now it's going to, this side over here is going to fall, and this side over here is going to rise up. So we can find the next step is to find the angular acceleration of this system. So again, we have to first find the rotational inertia of this whole system. Now, the way we do this is a little bit tricky. We have to basically add the rotational inertia of the left half of the board to the right half. So let's ignore these two blue masses for a second and just try to figure out the rotational inertia of the board. So that's what we're doing here in step 2. So the way we do this, you can think of breaking up this problem or this board into 2 pieces, the 4 meters over here and the 2 meters over to the right. The total mass is 45 kilograms, and this is twice this part here, all right? So it's basically 2/3 of the mass. So this must be 30 kilograms, right? 2/3 of 45. And this part over here must be 15 kilograms. The next thing to do is to use, again, we have to look at the table for rotational inertias of an object. This is basically a beam or a rod rotating about its end. So we're going to ignore this right part and just think about this piece sticking over here to the left. So we have 1/3 mass of the left times the length of the left squared. This is the formula I get from the table, 1/3 ml squared for a beam rotating about its end. So we're going to treat this separately, and then this one over here on the right, think of this as another beam rotating on its end here, and it has a mass of 15 and a length of 2. So multiplying these numbers and adding the terms, we end up with the rotational inertia of this beam to be 180 kilogram meters squared. Then we can find the rotational inertias of the 2 masses on each end. This one here and this one over here. That is exactly the same as we did for the previous problem. It's m1 r1 squared plus m2 r2 squared, which gave us 560. So the total rotational inertia of this whole system is now equal to the rotational inertia of the beam or the board, 180, and then the 2 masses, 560. So that gives us a total I of 740. So finally, we can solve Newton's second law. Torque equals I alpha. Therefore, alpha is equal to torque over I. The torque is 49. All right, remember we found this in the previous slide. And the total rotational inertia of the system is 740. So that gives us a total angular acceleration of 0.066 radians per second. We also looked at this problem briefly in a previous section with a leaning flagpole, and we calculated the total torque due to gravity on the flagpole. Now we're going to just take this a step farther and find out what the angular acceleration of this flagpole is if it broke off right here at the ground. Let's say it snapped because because of all the torque, and it started to fall. We're going to find out what is the, as it falls, it's going to rotate basically. So we're going to figure out what its angular acceleration is as it begins falling. So the first thing is to figure out what is the rotational inertia of this flagpole. So again, we have to resort to the table in the textbook or in your notes. And so this is a rod. Again, you can model this as a long rod or pole, and it's going to rotate about the end here. We're told that it falls but doesn't slip. So this is the pivot point down here. The flagpole is going to rotate as it falls down about this point. So for a pole rotating about its end from the chart, we have I equals 1/3 ml squared. So plugging in the numbers here, the mass of the pole is 200 kilograms. The length we were told was 10 meters. So that gives us a rotational inertia of 6,660. Now, step 2 is to figure out the net torque. Now, we did this in the previous part of the lecture, so I'm not going to go over the details here. But basically, remember the key for a long extended object like this is we take all of the weight of this object, in other words, mg, and we apply that weight force pointing straight down at the CG. Now for this flagpole, the CG is going to be exactly halfway along the length of the flagpole because the CG is the center of gravity, or the sort of like the balance point. So we know that the CG is 5 meters from the bottom of the flagpole. All right. The other thing we can calculate here is we know the angle. We were told this angle is 75 here. Remember, this angle is 15, and we can figure out this component of the weight force. This is mg times sine of 15. So plugging in all these numbers for the radius being 5 meters, the mass 200 kilograms, g is 9.8, and then we have sine of 15, which is 0.26, we get a total torque of 2,548 Newton meters. So finally, using Newton's second law, torque equals I alpha. So the angular acceleration alpha is the torque, which is 2548, divided by I, which is 6660, and that gives us an initial angular acceleration of 0.38 radians per second squared. We talked about ropes and pulleys earlier in this chapter as well, in one of the other parts of this chapter's lecture. And now what we're going to do is apply that to a system and figure out the rotational dynamics of that system using Newton's second law. And so these problems are going to be involving objects connected together using ropes and pulleys. So just a couple of the concepts here that we're going to use. The rim speed, in other words, the speed of an object or the rope along the outer edge, is equal to omega, which is the angular velocity in radians per second, times the radius of the pulley here. And likewise, the rim acceleration, A, is equal to alpha times r. The other thing is that, remember that the object here is going to move with the same speed as the rope does. So the speed of the object, therefore, as we just calculated up here, is equal to omega r, and the acceleration of the object is equal to alpha r. So let's just start with a couple examples here. The first one here, we have a string wrapped around a cylinder, and it's pulled with a force of 15 newtons. Now, we're given some information about this cylinder here. It has a radius of 10 centimeters, and it has a mass of 25 kilograms. So we can kind of predict, what's going to happen here. If we pull on this string, we're going to basically, the string's going to unwind here, but it's going to rotate this cylinder here on its axis. And of course, this cylinder, remember, it has a lot of mass, right? It's 25 kilograms. So it has rotational inertia. So this thing, is going to have resistance as you pull on it. And so we're going to basically, we'll calculate the acceleration and so forth and the rotational dynamics of the system. So there are actually 5 questions here, A through E, that'll kind of take us through this problem. So the first question asks, how much torque acts on the cylinder? Well, if we know that we're pulling on this string with 15 newtons of force, that was given to us. So if you think of this, looking at the end of the cylinder, here's the radius of the cylinder here. Here is the pulling force straight down. One thing about when a rope is wrapped around a cylinder like this, the tension is always at right angles to the radius here, going from where the rope attaches and to the center. So in other words, this radius I've drawn here is at right angles or perpendicular to this force. Now that's a good thing because remember, torque is the product of the radius times the perpendicular force. So it's just equal to the radius times the tension. Now let's be careful of our direction here. Notice that this cylinder is going to rotate in a clockwise direction, which is negative. Likewise, this torque is a negative torque. So the torque on the cylinder is negative R times T, where T is the tension. So 10 centimeters is 0.1 meters times 15 gives us a torque of negative 1.5 Newton meters. Part B says, what is the moment of inertia of the cylinder? So we have to basically look up this shape in the table, and it turns out for a solid cylinder, the rotational inertia, I, is equal to 1/2 mr squared. So plugging in our mass, which is given, and our radius, which is given, of course we have to convert it to meters, we get a rotational inertia for I of 0.125 kilogram meters squared. Part C, what is the angular acceleration of the cylinder? Well, here we're going to apply Newton's second law in its rotational form. So torque equals I alpha. Alpha is therefore torque divided by I. So I have minus 1.5 for torque and 0.125 for I, which gives me an angular acceleration of negative 12 radians per second squared. Again, this minus sign here just means that this thing is speeding up, but it's speeding up in the negative direction. It's going in the clockwise direction. That's why we have a minus sign there. Part D, what is the angular velocity of the cylinder after 3 seconds of pulling? So now what we're doing is we're going back to one of the earlier parts of this lecture where we did rotational kinematics. And we're trying to figure out what is the final omega, or angular velocity of the cylinder. Well, its initial angular velocity is 0, so the final is just equal to alpha times time. This is one of those, we had several equations for rotational kinematics that we're using here. And this is the one that would apply. We know what alpha is, it's negative 12, and we know the time was given as 3 seconds. So negative 12 times 3 is negative 36 radians per second. Now again, what does the minus mean? Well, think of the direction this is rotating. It's rotating in a clockwise direction, which is in the negative direction for rotation. The final question here, what is the acceleration of the hand? So you're pulling here with 15 newtons of force. How fast does your hand accelerate downward as you pull with that force? So remember from the previous slide, the linear acceleration A is equal to the rotational or angular acceleration alpha times the radius. So we have 12 is our, I'm finding the magnitude now of the acceleration. So I didn't include the minus sign here. So I'm just going to use 12 and multiply it by the radius, which is 0.1 meters, and I get 1.2 meters per second squared. Obviously, this acceleration is pointing downward because that's the direction that the hand is moving. This is kind of an interesting problem and application of rotational dynamics. It has to do with lifting a cylinder with a string. If you take a string and wrap it around and around a solid cylindrical object, for example, in your house, if you have a can, like a food can, canned food, soup, beans, something like that, and you wrap a string around it, you can pull up on the string, and if you pull slowly, not much is going to happen. The string is just going to unravel, and the soup can or whatever will roll on the ground. But if you pull up fast, you have to pull up pretty quickly. You can actually lift this whole object off the ground. So we're going to analyze this problem here. A solid cylinder of radius r and mass m has a string wrapped around it as shown. Find the acceleration of your hand necessary to lift the cylinder off the ground. So here is a free body diagram of our cylinder looking at the end. Notice this is the string force, the tension in the string, which is basically what you're pulling with here. And then the weight of the cylinder, remember, is going to act at the center of gravity, which is going to be right in the middle, right in the center of this soup can. So I've got the mg force acting down here. Now, in order to lift the cylinder, the force F must exceed the weight of the cylinder. So we have to have F greater than mg. So let's use Newton's second law now for rotation. So net torque on this cylinder is equal to I alpha. And from this picture, you can see that the only torque is this force here. Gravity does not create a torque because gravity is acting right at the pivot or axis of rotation. And so there is no torque there because there's no distance from this position. But this string tension, due to the force from your hand, does act at a distance r, which is the radius of the can or the cylinder. So the torque on the left is equal to F times r. And I, again, this is a solid cylinder. We've seen that a couple times now. Its rotational inertia is 1/2 mr squared, and then we have alpha here. Now, we learned up here that the force F has to be at least equal to mg. So let's set F equal to mg, which will give us the lower limit of the solution. So we're going to replace this F here on the left side with mg. We're going to replace alpha here with A over R. Now, where did I get that? Well, remember a couple slides ago, we said that A is equal to R times alpha. So therefore, alpha is equal to A divided by R. So I've made that substitution here. You can see I've replaced this alpha with A over R. Now we can do a little bit of cleanup. This R squared here, one of those R's cancels this R here. So on the right side, I end up with 1/2 mRA. And now notice on both sides, I have an R. So I can cancel those. On both sides, I have an M here and here. I can cancel those. And I'm left with, on the left side, just G all by itself. And on the right side, 1/2 times A. So I have G equals 1/2 A. And remember, we're trying to solve for what is the acceleration of your hand necessary. So solving this for A has, would be equal to 2G, but remember that it has to be greater than or equal to this. So our final answer is this. In order to lift up this cylinder with the string wrapped around it, we have to accelerate our hand greater than 2 times the acceleration due to gravity, where in G, of course, is 9.8. So this would be something, if you're curious about this, you can try this at home with a, get a solid cylinder like a can of beans or something like that would probably work. So here's our last example of this chapter. And this one we have another cylinder here, solid cylinder with a string wrapped around it again. And this time we don't have a hand pulling it, but we've got a mass hanging here that's going to create the force and the torque that's going to get this thing to start rotating. So the hanging mass creates torque, which causes the cylinder to rotate. How long does it take the small mass to fall 1 meter when released from rest? So in other words, if we release this mass here, it is going to fall, but remember it's got the string attached to it, and that string is going to unravel and unwind and get the cylinder to rotate. So this is a combination of a dynamics and a kinematics problem. So in order to solve the kinematics, in other words, find out the time and things like that, we have to first do the dynamics and figure out what is the angular acceleration of this cylinder so we can figure out the acceleration of the hanging mass. Now, this is interesting again. This problem is either very difficult or relatively easy depending on how we attack it. We saw this trick in chapter 5. This is an example of interacting objects again. And so for interacting objects, there's a hard way to do it, which interestingly your book shows you in your textbook. But there's also a much easier way to solve this problem, which is the path that I'm going to take and show you next. So as we saw before in chapter 5 with interacting object problems, the easy solution is a trick where we treat the objects that are interconnected, we treat them sort of as a single system. So the cylinder and the hanging mass is going to be considered our single system. We're going to first find the rotational inertia of the entire system. Now, this is not super straightforward, but what we have to do to find the rotational inertia of the whole system is we have to do it in pieces. So first we have the cylinder here. Well, that's easy enough. The rotational inertia of a cylinder is 1/2 mr squared. Again, we get that from the table, and we've seen this result several times already in this chapter. Now, what about the hanging mass? At first glance, you might think that it doesn't rotate, so it doesn't contribute any rotational inertia, but that's not right. The mass is part of this system which is rotating. So you can think of if we shorten this string, imagine making this string really short. So the system hasn't changed at all right? We're just shortening the string. So now the mass is basically part of this cylinder here. And we can see that this mass is a radius r from the center of the axis of rotation. So as this thing starts to fall, it is in a sense rotating. All right, so that's one of the tricks here. Now remember, for a compact object, its rotational inertia is just mr squared. So plugging in all of these numbers here. By the way, this mass here is uppercase M, that's the cylinder mass, and the hanging object is lowercase m, all right, that's this m here. So I plugged in all those numbers and came up with our rotational inertia of 9.45 times 10 to the minus 4. The next step is to apply Newton's second law for rotation. Net torque equals I alpha. So alpha is equal to net torque divided by I. And the net torque on this system, well, here we've got this hanging mass again at a distance of r, all right, from the center. So that's going to be r times the weight of the hanging object, which is mg. And the minus sign, because of the direction of rotation, is clockwise. So again, I can plug in all these numbers now that we know, and we come up with an alpha, angular acceleration of negative 124 radians per second squared. We're done now with the dynamics. The last step here is just to do the kinematics of the problem. We know that the object here is going to accelerate at the same speed as the rim up here, that is the rope that's unwinding. And so remember from a few slides ago, the acceleration of the object is equal to the radius times alpha, which is the angular acceleration. So the radius is 0.03 meters, all right, that was given up here. And our alpha is negative 124. So our acceleration of this falling object is negative 3.73 meters per second squared. That's how fast it's accelerating downward as it falls. And then the final step here is to figure out the time for it to go 1 meter. So here we're going to use, remember the distance formula for an object that starts at rest. The distance that something moves is 1/2 at squared. So solving for t, I get the square root of 2d over a, and I can plug in my numbers. The distance is -1 meter. All right, that's where it's falling. That's why it's a -1. And the acceleration is -3.73, as we just calculated here, which gives us a total time of 0.73. So that is our lecture from Chapter 7. I will see you shortly in Chapter 8. Goodbye.